you have linear momentum, if they want angular momentum, they will specify angular momentum. If they just say momentum, that's just this. Okay. So it's a vector quantity. It is in the same direction as your rotational velocity. So use your right-hand rule to figure out the direction of angular momentum. It's always going to be the same direction as your rotational velocity. This equation is valid when you are taking the angular momentum about the axis of rotation. So if these two both have the same axis of rotation, that okay equation. Okay. The units, just like regular momentum, they're rough. There's no, I don't know why we don't have a scientist name. Just like, hey, let's just make this easier. Regular momentum is kilograms. Meters per second. Smiley is not going to hold water. And then angular momentum is kilograms meters squared over seconds.
We'll just name it Steve. I have 12 Steves in the
All right. So. So net torque is equal to I alpha. We know that alpha is equal to the change in angular momentum or the change in time. So we can say alpha this is one expression. If we don't change the shape, is change in angular momentum. So the net torque, one way to describe that is the rate at which angular momentum is changing is equal to the net torque acting on an object. We can bring this over here. And we can say that this isn't a technical thing, but I've seen it brought up. Rotational impulse, there's not really a variable for that. But this has parallels to regular momentum. Where the net force is equal to the rate at which momentum is changing. This is actually how Newton wrote his second law. It wasn't this. The rate at which momentum is changing. It's actually more powerful, which we'll see at the end of the semester, than that. So this is impulse, regular impulse. Okay, so this is rotational impulse. Assuming if your torque is constant. A little foreshadowing there. Okay, you can use that if torque is constant. You can use that impulse if force is constant.
I cannot foresee this going wrong in any way.
Okay. Good with that? Here we go, the slope, as we just discussed. the rate of change of changing L over changing T. Yeah, skip over these. We're doing okay. So, what? All right. You all. We want this spinning this way. Yes. Yes. Okay, what I want you to do is just do this. Like you're just pulling this back and pushing that forward. Okay? It's the weirdest thing. Definitely a weird one. The faster you do it, the weirder it gets.
Hit him in the head.
Yeah.
Something looked like Jim Carrey was like trying to fight himself.
Is this for churches? Is this just like acceleration? Speed it up. Oh, sure. Nope, there's nothing. We just stop that.
That'd be the rate of change for the rate of change.
You're into that one.
I think that's like the only thing we use that for. I'm back. That would actually push the I would go stand on the platform.
I know, that's
I did that. I
would have gotten yes.
God. You guys are so.
I saw it. I didn't just think it was mine. I was like, who's the license?
I guess.
So,
Inertia.
all right. So when we applied, so it's spinning this way, okay, and you pulled with this hand and pushed with that hand, okay. So what is looking at the top view? Okay. What is the direction of the torque from your hand, from the orange arrows? Right? You wanted it to pivot this way. So looking down on top, so the direction of the torque technically is out of the page here. That's what you wanted it to do, okay? So X into the page, dot out of the page, yes, three-dimensional vectors. Okay, you did that with right-hand rule stuff, okay? You're looking at the arrowhead, you're looking at the feather, okay? So here, the torque is going that way. Yes? Okay. Now, The direction of the angular momentum is which way? Initially. Of the bicycle, sorry, of the bicycle wheel. The bicycle wheel, which way is it going? So here it's going this way. Going to the left. And going to the left. Good. So that is our initial angular momentum of the wheel. Okay. When we applied a torque for a certain amount of time, it's going to cause a certain change. Oops, let's not do that. It's going to cause a certain change in angular momentum. Whatever the direction of the torque is, that's the same direction as the change in angular momentum, which is going to be equal to final angular momentum minus initial angular momentum. Okay with that? Okay, so when we apply a torque to that going this way, it wants to cause that change in angular momentum to go that way. So our, just looking at our directions here, okay, so the direction of the change in angular momentum is also this way. It's hard to draw there, but okay with that. So when we find the resultant of these two, we do head to tail. See what I'm doing there? Head to tail, okay. The final angular momentum is that way. Okay? And when you did that, and that's hard to draw there. When you did that, what did the wheel tend to do? So I'm pulling this, pushing that. It tended to
Rotate.
That's what it. I'm trying to push it this way and pull it this way, but okay, does that make sense? And so it tends to go. Whoop. You good with that? Okay. Questions? Weird. Go.
Is that the same thing as like spinning out on a bike? How they like do the like I don't know, when someone's like crashing on a bike they like dip and then like do some kind of like weird spin out.
It's gonna lots of bike crashes. I'm not sure which one you're referring to. So there is people say that angular momentum is the reason why bicycles work, how you can like steer with no hands. It plays a factor, but it's definitely not a big factor. They've made bicycles where they've actually had two wheels in the front and one was made to spin the other way at the same speed so they counteract and you can still ride a bike with no hands.
How does that?
It's the back wheel. It's on the back.
So,
So when you apply that torque and there's new final momentum, the wheel goes that way and then stabilizes itself, or you restabilize it?
as long as I was exerting torque, it is changing. So once I stopped trying to push it, then it restabilizes. Good with that?
Sure.
Why not, right? Wacky stuff. All right. So here you've got a ball going around a horizontal circle, constant speed, okay. Angular momentum. What would be the angular momentum of a point mass? mr squared. And I've got a constant speed. Should have put a little v there, script v. I need to express this in terms of v. So that's going to be v over r. So that's going to knock out that, and you're left with this expression. Okay, this is. Does that make sense? Where that came from? So the question is, if you let this ball go, would it still have angular momentum? About point C. The weird thing is, okay, so you have a ball moving at a constant velocity this way. What is the angular momentum about point C? So what we do is draw a line of action. We move the velocity vector as close to the axis that we're referencing as possible, which makes a perpendicular radius. Okay, which is the same expression as if it was moving and spinning in a circle. And so this ball here has this angular momentum about point C. Okay, even though it's not rotating.
I think that falls apart if the velocity is changing.
Yes, that's an instantaneous angular momentum at that point. Just like its momentum would be different if the velocity was changing.
How does that like help us know every time like at a single point in time?
Because usually it's constant, because its inertia wants to do that. You would have to have a force acting on it to make it do something not constant.
Okay.
Okay. So we use this expression for a point mass revolving about a point outside of the point. What do I mean by that? This is like what the Earth around the sun. We do this equation when axis of rotation is in the object. Or goes through the object, maybe goes through the object, that's probably a better way to say that. I know that's the wrong way to spell through. Kind of like the Earth in 24 hours. Okay. So if you So does that make sense, the distinction of when you would use which equation? Okay, this is the best example I like. All right. So the Earth isn't a point, but you can model it as a point compared to the sun. So anytime you get something going around outside, like the axis of rotation, the pivot point, the reference point is outside the object, do this. If it's in the object, within the object, do that. Yeah. Make sure your moment of inertia agrees. So if it's not going through the center of mass, then you're doing the parallel axis theorem with that. Good there? Yeah. Everybody get out of the page. Okay. Kid's running this way. If she grabs it on a rope or strings, you end up going like this. Yeah? Total angular momentum of the system is conserved if net external torque is equal to 0. Net external torque is equal to 0. Memorize that. But more importantly, know how to use it.
Is there ever a situation where like we're given a linear velocity but we can use conservation of angular momentum instead of just regular conservation?
Okay. So the classic is the ice skater, where you are doing a certain angular momentum, have a certain moment of inertia, have a certain angular velocity, and then I bring them in, and I spin faster. Was there any external torques? Nope. So the angular momentum is conserved. Ah!
Okay, there you go. Now he's moving.
Okay. So before and after, it had the same angular momentum. Initially, it had a greater angular momentum and a smaller angular velocity. Afterwards, I reduced my angular momentum, increasing my angular velocity. Look at that. All right. So we are okay. So we're going to change this a little bit. Instead of shoving it this way, we're going to shove it this way. That makes sense? So let's that's why that's from. Stripped. That's a sad day. Yeah. Well, let's figure out what it does first. And then we'll demonstrate.
Because it might go flying.
Okay? So, which way? This is still that. This is going this way. Top view. Side view. Okay. So, which is going to be the same direction as your change plus your initial is going to be equal to your final. So your final is going to be doing kind of like this. Yes? Okay.
We're switching to
So that makes it kind of like, wait a minute, do that, and that makes it do, I don't know how to draw that. All right.
I don't know.
Okay, which, here's your thumb, it starts making it do this.
Rotate out.
Okay, make sure we get this right here. That goes up, that goes down.
Oh, yeah.
Did it do it?
It's gyroscope.
Cool that. Okay. So that's like the hardcore. Let's. But you see why that did. I mean, you've seen that demonstration, I'm assuming, before. But you get, like, I rotated, I started to spin this, like I was doing this. Does that make sense? Crazy, yeah? Yeah. I want you to try this. Okay. Try to do this in the inner class. All right. So when is momentum conserved?
Force.
No net external force. When is mechanical energy conserved?
We know non-conservative work.
There's no non-conservative forces doing work. Antonio.
It's kind of like so when you spin something that like kind of falls and kind of bring out when it's spinning fast.
Yes.
Is that because it takes less energy that way? Because instead of like keeping it smaller and inertia and spinning faster, like that would be more energy than just the ball spinning out.
Ooh, I never really considered from an energy point of view. I think less energy. I can tell you from like that's the way momentum wants to go. Like the momentum once it starts moving wants to go in a straight line tangent to the circle, and it can until the tension's tight enough to say nope, stay in the circle. So like if you're looking down on top of it as it spins, it's kind of doing that until it gets tight enough where it's like nope, you stay in the circle. From an energy point of view, usually this axle is connected to a drive shaft, like there's an engine or motor saying spin this way. And so from a conservation of energy point of view, it's not being conserved because there's work being done.
Yeah, but it has less energy than
Yes, there is less.
this size.
It doesn't because it's still going to spin at the same speed as it would have. So it actually has more, but that's because there's more energy given to it by the shaft. If that does that make sense? I do see, like, okay. So have you ever? I'll give this to you. Have you ever been twisted up in a swing?
Yeah.
And like let it unspin. And it's hard to bring your feet in. It's easier for your feet to go out. Assuming that the rope isn't causing more torque, which it is, and you're just spinning there, that would be there'd be less rotational energy. Like if you're in outer space and you're spinning, like, and then like that would be your relaxed position, like just spin a little slower. Okay. All right. Good transition.
He's gonna launch the pen.
All right.
We're gonna shoot the pen.
So this is a classic.
Oh, yeah, we are.
I'll just do it from here.
Yeah, that's a good.
This is a classic demonstration. They used to do this back in the day with bullets, like 22 rifle, and then you got illegal to bring guns to school.
Specialized machine to do it.
So they,
Front of 22 cars.
so what they would do is they'd have this massive target of clay suspended, and they would shoot. This would be a gun, and they would shoot. Oh, could someone rotate the camera towards this way? Okay, so when they shoot it, the bullet impacts and stays in the clay target, and then they measure and shoot it. So we start with how high up it goes. And the objective is to figure out what the muzzle velocity of the gun is, the bullet as it leaves the gun. So I pose that to you. How would you go about doing that? I'll give you a hint. You need to break it up into stages and figure out what's conserved or what is conserved when. Assuming no friction, we'll say this is spring-loaded. It is. Okay, no friction, and the ball has left the gun before it hits the target. So figure out what's conserved when.
So the theory of the momentum is that like is relative to that axis anywhere. That momentum is that you can go from that to whatever momentum it has to get there. So then you can look at
The energy.
then you can look at energy because when it hits it, right?
That's all
then-
into kinetic energy.
yeah, so then it's all kinetic and it goes all into central. Yeah.
They can solve for the initial velocity after it's been hit.
But the energy conserved is yeah.
In theory, the spring is a converter. All of them. And everyone converts it to potential energy. Yes.
Yeah, so you would take that to your final velocity, your height that's up there, that's your potential energy, which can let you find the velocity that it has when it hits the pendulum. And then you can take that velocity when it hits the pendulum and use momentum to find the initial velocity when it reaches it, right? Because momentum is conserved relative to the points.
Hopefully you have discerned that there are 3 stages. You get the launch. What's conserved during the launch while the bullet's still in the spring-loaded gun? Yep. Mechanical energy. Mechanical energy conserved. Mechanical energy is conserved. Good with that? During the collision, what's conserved? Momentum. Is mechanical energy conserved?
No.
No. Why?
Because it's an inelastic
Because it's
collision.
an inelastic collision. It sticks. We lost kinetic energy. Okay. And during the swing part, what's conserved?
Nothing's conserved.
Mechanical energy. Okay. Good with that? Now, this is true if the Are we good with that?
Yep.
What would happen if we hit a rock that was massive?
Angular momentum. So to move the velocity vector over to
So give this a shot. Yeah, we'll crank through this and then we'll give it a turn and drive down on the platform. Do what? The moment of inertia of a rod at the end of that is 1/3 ml squared. Okay, first off, during this, so we're not really worried about the launch part. During the collision part, is regular momentum conserved? Why or why not? Is linear momentum conserved?
No,
Why not?
because the rod isn't allowed to like move, it's fixed by the center. There's not, the center mass is not allowed,
Why?
because it's fixed in place.
By? Okay, there's a pivot that is exerting an external force. The hinge prevents the center of mass from doing whatever it wants to do as an external force. So momentum is not conserved. But what about angular momentum? Is angular momentum conserved?
Yes.
Why? Why is there no net torque?
because the force of the axle is like in the center of rotation.
Right. The axis of rotation that we're looking at is the hinge. So even though it exerts a force, there is no moment arm. There's no lever arm. So no torque is exerted. Okay, so that collision, you're gonna look at angular momentum being conserved of the system. So you've got this point MVR is L. Okay with that? Afterwards, you've got think of what your expression for this is the system of the rod and the block. What is your system of angular momentum going to be right after the collision? L of block initials equal to the L of the block final plus L of the rod. Fine, yes? Okay. So this is MVI L is equal to M negative VF. Going backwards. L plus, bless you, I omega. You okay with that? So we would get yes, or not squared. Okay, so we'd have that expression. And then, once I get final rotational speed, so that's how fast it's going right here, right after the collision, what would I do? Conservation of energy. Now watch this. This is important. Is everybody okay with that? Like, I don't want to just leave it like pull out premature, but here we've got 1/2 I omega squared is equal to mgh. This is that. Okay. But h this is important. When we're talking about rotational stuff, this h is the center of mass, how high the center of mass rose. That's super crazy important. Subtle, but they'll nail you. Okay. How high the center of mass rose. Good with that. And then from that, you can figure out the angle with geometry. How are you with that? Full on.
And the axle or angle it rises, is it talking about like from where it started? Or
Yeah.
like from
Usually it'll say from the vertical. So like it'll be that angle. Okay? Good? All right, if you'd like to write on the